Welcome to The Explainer. You know, if you're joining us today, it means you've got this incredible ambition. You actually want to build the future of technology. But as you're standing right here at the edge of your academic journey, you're facing a massive decision. I mean, which path do you take to actually get there? Well, today, we're basically stepping in as your personal career advisor to break down one of the absolutely most critical choices in modern engineering: computer science versus electrical engineering, and of course, that really powerful hybrid path that connects them both. So here is our roadmap for today. First, choosing your tech path. Second, software versus physical hardware. Third, inside the engineering curriculum. Fourth, the lab and the office. Fifth, high salaries and top industries. And finally, number 6, building the future together. Section 1. Choosing your tech path. Navigating the future of technology. Okay, let's dive into this. Do you want to write the code or do you want to build the machine? I mean, this is the ultimate question, right? Do you want your career to exist in that abstract virtual world of software, or do you want to get your hands dirty in the physical, continuous world of energy and hardware? Section 2. Software versus physical hardware, the Great Divide. Let's clearly contrast these two traditional pillars. On one side, you've got computer science. Now, this is a field born straight from mathematics. It's highly theoretical and literally entirely software-driven. You're dealing with abstract algorithms, discrete math, and virtual layers. On the flip side, you have traditional electrical engineering. This grew out of the physical sciences. It's incredibly hands-on, heavily reliant on physics, electromagnetism, analog systems, and continuous math. You know, things like calculus and differential equations. Put simply, CS is logic, EE is physical energy. Now, what's really interesting about this slide is how it brings us to the ultimate middle ground: electrical and computer engineering, or ECE. ECE is a true hybrid discipline. It seamlessly connects the physical silicon of electrical engineering with the low-level programming of computer science. It integrates both discrete and continuous mathematics into one package. As an ECE student, you don't just learn how to write code or how to solder a circuit. You learn hardware-software co-design so you can build really complex cyber-physical systems. It's the whole shebang.
Section 3. Inside the engineering curriculum, the academic journey.
So what does this actually look like in practice? Well, after your foundational first year of calculus and physics, things get incredibly specialized. In year 2, you really start bridging the physical and digital. You'll take advanced math alongside electromagnetic theory, while at the exact same time taking computer science courses in data structures. Moving into year 3, it's all about system interfacing. You go from separate, isolated components to unified, embedded systems. You're going to program microcontrollers using assembly in C, physically interfacing with sensors and actuators. And finally, year 4 is all about your capstone design project. You'll work in a team to design, simulate, and literally build a physical real-world prototype, like an autonomous robot or a bioelectronic diagnostic tool. Listen to this fantastic quote from Victoria Aguirre, an engineering student at USC. She mentions how the program blended hands-on circuit building with software engineering and highlights being welcomed into a tight-knit group of bright-minded thinkers. And honestly, this brings up a vital piece of study advice. Engineering is a team sport. Programs are usually structured around tight-knit cohorts of about 50 students. You will absolutely lean heavily on these peer networks and study groups to get through those really intense lab sections. Collaboration is for sure the key to surviving and thriving here.
Section 4. The lab and the office. A day in the life.
And this brilliantly illustrates the difference in your actual day-to-day working environment. If you go the pure computer science route, your life is heavily office and cloud-based. Your tools are software compilers, integrated development environments, databases, and web servers. But if you choose electrical or computer engineering, your world is the dynamic hands-on laboratory. Your daily tools are going to include oscilloscopes, multimeters, spectrum analyzers, logic analyzers, FPGA boards, and physical robotics. You are physically testing and, let's be real, occasionally breaking hardware, not just debugging virtual code.
Section 5. High salaries and top industries. The payoff.
Okay, look at this number, $103,222. That is the average starting salary for a Granger computer engineering graduate right out of the University of Illinois Urbana-Champaign. And get this, that is often paired with a median signing bonus of $10,000. The return on investment for choosing this educational path is just absolutely fantastic right out of the gate.
So the crucial point is, while both of these fields pay incredibly well, there are very clear avenues for career growth. Average base salaries for electrical engineers sit comfortably around the $80,000 mark, while software engineers average over $100,000. But as you specialize, particularly in those hybrid ECE roles that integrate AI or embedded systems, you move into principal engineering roles where salaries can easily soar past $158,000 a year. That's serious earning potential.
And securing these jobs is highly probable. Elite engineering programs regularly boast placement records as high as 97%. Plus, for our international students watching, this is huge. Degrees in these specific fields qualify for the 24-month STEM opt extension in the United States. That means you get fantastic opportunities to stay overseas, gain invaluable global market experience, and launch a truly international career.
Because of this skill set, you will be fiercely recruited by a wildly diverse range of top-tier service sectors and corporations. We are talking about tech giants like Intel, Microsoft, and NVIDIA, aerospace leaders like Boeing, and massive telecommunications and electric power companies. Even fintech aggressively hires these engineers to build the lightning-fast hardware and software networks required for algorithmic trading. The demand literally spans the entire globe.
Section 6. Building the future together. The next frontier. Let's move to and see how this builds the future, because the absolute cutting edge of technology demands that these fields merge. Modern marvels rely seamlessly on both disciplines working together. You can't have the Internet of Things without physical wireless sensors and cloud software. Artificial intelligence requires massive software models, but it actually runs on custom-designed silicon chips. Surgical robots, smart renewable energy grids, and the completely mind-bending world of quantum computing, these all require engineers who deeply understand the bridge between the physical and the digital.
So, the choice is yours, and honestly, it is a thrilling one. Will you choose computer science to write the abstract code? Will you choose traditional electrical engineering to build the physical power systems? Or will you choose electrical and computer engineering to unite them both and build our cyber-physical future? Whatever path you choose, the world is literally waiting for you to build it. Thank you so much for joining us on this explainer, and we will see you next time.